All right, let's take a brief look here at electromagnetic induction. We've already gone through the creation of electric fields from charges and creation of magnetic fields from permanent magnets as well as from wires. And now we are looking at some of the interesting effects that come with moving currents or at the same time changing magnetic fields. There's some interesting names in this area. Michael Faraday was actually the first one to notice that a magnetic field could induce a current in a circuit. He was an extremely talented physicist, and he observed while having if you take a ring, an iron ring, and wrap some wires around one side of it, connected to a battery with a switch. Actually, here, let me draw it for you. Okay, so we're going to draw our ring here. I wonder if we can make that thicker. Highlighter. Change the color. Do that. I don't know, make that ring. We want to have a nice thick ring here. You'll pardon my drawing skills. Okay, now we're going to wrap on one side of that. Take a wire, wrap it around that ring, number of turns around that ring. And bring that out. We'll have a switch here and a battery. Okay, we've got a voltage and a switch, and then on the other side we'll put some sort of a meter that measures current. Faraday wanted to create a current flow in the left-hand side and have that induce a current through the right-hand circuit. Okay, so by closing this switch here, and of course your circuit essentially has a resistance R to it. Okay, and that voltage will create a current flow I in this current, which as a result of the wraps of the wire there, as we saw when we were calculating magnetic fields from coils, B equals mu 0, the number of turns per unit length times the current flow, and we get a magnetic field produced in this coil. Magnetic field going down through here. Okay, because there's an iron core in there, that magnetic field predominantly propagates around through the iron core because of the permeability of iron is better than air, so it's as if the iron it likes to be in the iron. The magnetic field prefers to be in the iron than it does in the air. At any rate, that will create a magnetic field through this coil on the right-hand side. And Faraday was hoping to see that they would create a current flow in that right-hand circuit. And Faraday noticed that it didn't. He closed the circuit and we didn't get a current flow in the right-hand side. But he was a good enough experimentalist and an observer, critical observer, to note that at the instant that he closed this circuit over here, the instant that he closed the switch here, there was a momentary blip in the needle on the ammeter over here. We could call it galvanometer actually, as a result of that. But once that switch was closed, the current flow, the needle went back to 0. And then if he opened that switch to stop the current flow in the left-hand side, then he noted again that there was a deflection in the needle in the opposite direction. And as a result, Faraday reasoned that it wasn't the magnetic field by itself that induced a current flow. Because remember, what this meter over here is saying that somehow there's a current being created in this circuit when Faraday opens and closes the switch. And that current is either going one way or the other, depending upon whether he's opening or closing the switch on the other side. So Faraday reasoned that it wasn't the magnetic field itself that was the important thing, it was whether the magnetic field was changing. Because if you think about when that switch closes, it takes a brief time for the current to go to its maximum value, and therefore this magnetic field being induced in the coil is increasing or decreasing depending on whether you're turning closing the switch or opening the switch. So if B is changing, that was the important thing, not whether B was present. So we'll get into the mathematics of that in just a second. I want to point out that a couple of people whose lives were affected by Faraday's work in the early part of the 1900s, so Thomas Edison, obviously inventor of the light bulb, and Nikola Tesla, who worked for Edison. I believe, put it this way, Rockefeller, who made his fortune in oil, Amoco, American Oil Company, was no fan of Edison because Edison, as the inventor of the light bulb, was a proponent of electricity, and obviously Rockefeller, being an oil man, was a proponent of lighting by oil. Well, nevertheless, ultimately, Rockefeller did okay. Edison envisioned light bulbs, in every house and every street corner, and the way to do that was, of course, to deliver the current over power lines. And Edison was a strong proponent of direct current, DC, and that meant that because DC required that you have to have small power plants in every neighborhood, because with a direct current you have a higher power loss in the wires, and he envisioned these power plants in every neighborhood. Nikola Tesla, who worked for Edison, but became disgruntled with Edison and accused him of stealing some of his ideas, was a proponent of alternating current. An alternating current requires less current to transmit the power, so you get less power loss through the wires, through the lines. Tesla made an acquaintance with Westinghouse, and the transformer was a new device, and the transformer is actually based on the Faraday law of electromagnetic induction. And with the transformer, Tesla showed that you could transmit power over power lines with a very small current but a very large voltage, and they would lose less power to resistive losses in the wires that way. And then you would need a transformer from pole to your house to take the voltage from 100,000 volts being transmitted through the wires down to 120 into your home. And so that's obviously what we have in our country. In the United States, we oscillate the alternating current at 60 cycles per second, 60 hertz. In Europe, it's I believe it's 50 or 55. It's different over there, and they have a different level of voltage. which allows them to use cheaper wires. Nevertheless, it's just different. Okay, well, let's move on to the next slide. So just to give you a brief amount of history there. Electromagnetic induction, we'll jump right to the equation here. We have the symbol for induced EMF here in volts. Well, that just says that, think of it this way. In the previous slide on the right hand side, let's go back to that. Over here, I want to circle that. So over here, this circuit over here has no power source in it, right? And yet, when the switch is closed, momentarily a current will flow around this circuit. So it doesn't have a battery in it, but we know that currents flow in response to voltages. Therefore, in our next slide here, you'll see we're just saying the voltage that's induced, we'll call this script E, is related then to the number of turns of the coil and the changing magnetic flux, delta over delta T, of this quantity, capital Phi, and capital Phi is the magnetic flux. And the magnetic flux is comprised of the product of the magnetic field times the area, cross-sectional area of the coil. The next picture here shows an example of a single rectangular coil immersed in a magnetic field that is coming out of the page. So we're looking at the arrowhead coming toward you, okay? And the area we're referring to, of course, is the area there, the cross-sectional area. In this particular case, it's x times y. This is a picture taken from your first problem in Mastering Physics there in the chapter on electromagnetic induction. So in particular, in this case, we would see we only have one turn, so n equals 1, okay, and the magnetic field would be given by the value of B here. And notice what happens if we have a fixed area here. So I'm going to put in the definition of the flux. Flux is B. It's not a very good B, is it? B times A. Okay. Now remember what the delta symbol is asking. The delta symbol is asking whatever symbol's next to it. Are you changing? So it's coming in here and it's asking B and it's asking A. Are you changing? And in the case of our picture here, with this fixed rectangular wire, the area is not changing. So we can bring that A outside the change symbol, delta, and just write this as NA, delta B over delta T. Okay. So there's our, in particular for this coil where the area is fixed, our only concern is we will induce an electromotive force, a voltage, I'm sorry. We'll induce a voltage, and we'll know we've induced a voltage because we'll find the presence of a current in this wire if the magnetic field is changing. So if the magnetic field is increasing, okay, then delta B over delta T would be positive, and that would induce a current in this loop whose resistance is R. And then notice that the current induced in this loop would be in such a direction as to try to diminish changing the increasing magnetic field that is being created by the changing magnetic field. That's Lenz's law. Essentially, you have to look at it this way. This little loop with this magnetic field through it is let's call it happy this way, the way it is. There's no current flow in it. The magnetic field's constant. So it's an equilibrium. It's a stable situation. If we change the magnetic field by increasing or decreasing it, current is going to try to flow around that loop in a direction, and use our right-hand rule, in a direction to try to undo the change in magnetic field that has been imposed upon it. Now, if this is our loop, and the current, and then the field is increasing, pointing toward me, then current's going to want to flow around that loop using our right hand to try to create a field pointing the other way to try to cancel the increasing field from the outside. Essentially, it's trying to maintain its original state. Okay. Once the increasing field stops increasing and gets at another value, a new value, the system essentially comes to equilibrium at that new value, and there's no more induced current because it's saying, okay, you're not changing, and I'm happy with what I'm experiencing here, and I've adjusted to that. Okay. I want to take a look here at problem 25.1, electromagnetic induction. So I need to jump back over here to Mastering Physics, and here we have it. Let's blow that up here. Okay. In this problem, we are told that we have a loop of radius 0.35 millimeters, okay, and a resistance of 0.038 ohms. Okay. Let's bring that information over to our final graph here. Okay, we've got all our information here for this problem. But let's go ahead and start this slideshow again and come up to our page. All right, here we are. Okay, we've got 35 millimeter radius down here, you'll notice. Let's get our pen up here. We've got our resistance in our circular wire. We've got this magnetic field pointing into the page, 1.1 Tesla, and we're told that it's going to be turned off at a constant rate to go to 0, and then while this happens, it'll induce a 0.2 of an amp current in the coil. Okay, so I believe the first question is which way will the magnetic field that is induced as a result of the induced current flow be pointing when the external field turns off? Okay. Now let's bring up Faraday's law here. Okay. Faraday's law. We only have one turn, so I'm not going to put N there, but that's delta phi, okay, flux, changing flux, okay? All right. Now, if this magnetic field is being turned off and the circle wire will have to create a current flow around that wire in order to rebuild the field that is diminishing. So we use our right-hand rule again. Remember our right-hand rule, take our right hand, and if the field is going into the page and it's diminishing, we want to come in and add to it. So we want to have a current flow that is going to go clockwise around that wire to create a new field to support the field that is diminishing. Okay? So if the current flow is induced around this wire in that direction, that will rebuild a magnetic field that is diminishing in the area circumscribed by that wire. Okay. Let's see. Now we've answered part A, which is that it points into the screen. The magnetic field points into the screen. That's our X's here, and that we have a clockwise current flow. So we've got numbers. So we want to calculate how much time. Okay. So we're being asked to find delta t, the time it takes for this field to diminish from its original value down to 0. Well, okay. Well, we know that the EMF is related to the current and resistance through IR, right? And we know that the flux is the area times the magnetic field. The area is constant, right? So we can bring that area outside here and write this as delta B over delta T. And let's go ahead and solve this for delta T. So bringing the delta T over to the left-hand side, taking the IR and putting it underneath down here, bringing the delta T over here, we get an equation that says delta T. And I don't really think we need to be concerned with the negative sign. We're not concerned at this point. We're just calculating the time, so we don't care about the direction of the current flow. So we're going to have A, let's see, the area of a circle is pi A squared. The magnetic field is going from, even if I keep that negative sign here, we're going from the initial value to the final value, so it's B minus B0, B final minus B0, and the current I and the resistance R. Okay, so if we go ahead and put in our numbers, we see, or let's just change the color here so we can see what we've got here. Okay. The final magnetic field is 0. The original one is 1.1. .035 is the radius. Okay. 0.0. We have to convert to meters. 0.35. Current is 0.2, 0.2 of an amp, and the resistance is 1.038, is it? Okay. Very good. And when we put that all in, we've calculated the time it takes for this field to drop from 1 to 0, given that we have an induced current of 0.2 amps. I think that's it.